Welcome. This is going to be a series of about 2 or 3, maybe 4 videos on request of my daughter for a class that she and her friends are taking or will be taking. And this may benefit some of my geometry students from last year who I know are going to be skipping pre-cal. So I've never done a calculus video before. In fact, the last time I did calculus was when Reagan was president. The Air Force didn't really require me to do too much calculus. I was mostly algebra 2 and below. So I'm a little rusty, but I can get there close enough for government work. All right, if you want something better, trust me, there is so much better out there on the internet than me, but I can use this as blackmail material. Now, what we're going to do is we're going to get a little bit of background on what an integral is. There comes in 2 types. We have the indefinite and indefinite. The indefinite is very commonly called the antiderivative. Now, let's go back to what a derivative is. A derivative is basically, well, there's other things to it, but if I were to take a secant line on this quadratic right here and draw a secant line, and I had 2 points, x1 and x2, or a and b, I would have a little bit of differential here. And what we're going to do is try and find the tangent line to that, the tangent equation of the tangent line right here, which is that secant. Well, it's not a tangent exactly because it intersects at 2 points. But what we do is we get that point just really, really close to where basically there's infinite, there's hardly any space in there. It's infinitely close to where we now are looking at the tangent slope of, say, this point right here. Now, given that we can find the derivative due to our power rule and other things, the antiderivative is going backwards. We're given this equation, and we want to go backwards and maybe find one of the possible equations for this original parent function or original function. So here we go. Derivatives. I'm going to presume that you're already experienced with derivatives. I'm not going to go into the theories or the deep definitions of them or any type of proofs. So basically, just to refresh, derivatives. Now, I'm not sure what your notations are going to be used. I've been to several different universities, and several professors have used different notations. Some people use this. I have used that before, probably I think in Hawaii. I use that notation. So, but I'm going to encourage you to use this notation right through here. This is going to help you out when you get into some more complex integrals. This one is very common right here. This is basically just an operator, a process of differentiation. This is more formal, where you're taking the derivative of x, the function of y in respect to x, and this is the same thing. Here is going to be very common, especially when I write a function like this, where I have y equal to. This is the derivative of y in respects to x, and the function, of course, is x to the third. The power rule is just simply this. You have x to the n, and when you do the power rule, the n is going to come to the front, and it's going to be n minus 1. So this is just simply 3x squared. Again, I'm presuming that you're experienced with derivatives. So what we're going to do here is go backwards. It's like an inverse function. That's why a lot of people call it the antiderivative, not necessarily indefinite integrals. So going backwards, we just kind of reverse this process. Basically, we're going to add 1. Here we subtracted 1. And to get rid of what we did here, we're going to do the opposite. We multiply by 3. We're going to divide by 3. All right? So basically, this turns into 3 into x cubed, because 3 over 3 is 1. Now, let's go ahead and take a look at an example. Boom. So we have our rule here for an indefinite integral. We're going to go back to the function, and we're going to add in this constant of variation. Now, I should have done that. I should explain that back here. I need to put a constant of variation right here. Because take a look at this. When I do these right here, I'm going to get the same answer, 3x squared, 3x squared. Because when I do this, this is just 4 x to the 0 power. The slope is 0. The slope is already 0. So when I take a tangent line of that, it doesn't really make sense. So it just goes away. This just kind of X's out. It doesn't matter what it is. If it's some kind of constant, 4, 7, pi, whatever, it goes away. So when I go backwards, which one am I going to? Am I going to this one? Am I going to that one? Am I going to the other infinite ones? There's an infinite number of answers here. So we just put in our constant of variation at the end. So we're not sure what C is, but we have an idea it's probably something. It could be 0, it could be some other number. So that's why we have the C here. Now let's go ahead and go backwards. We're going to add 1 to here, and we're going to divide by 5. Okay, so that's going to be 5, 5. So basically our answer is going to be x to the 5th plus c. Pretty straightforward. We're just going backwards from our derivative. It's an antiderivative. So here we have a polynomial, and the beauty of this is that we have this rule. If I take the integral of some polynomial, I could break it up into parts. I could do the integral of 5x cubed dx. Now it's important we put that dx there. This changed over the centuries. This first came out in the 1680s or something like that, or 1700s. And it meant a little bit something different, but today's standards, this dx actually can come in useful when we're solving some other integrals. But this is like a parentheses. This is my integral notation here, the sum, and this is where it stops. So I'm taking the integral of this. And then I'm going to take the integral of this. Well, that was a lousy one. And I have to put that dx there. Do not ever forget the dx. That would be a no-no. Okay? So on. Okay? So I'm going to take the antiderivative of each one of these separately. Makes it kind of easy. So I'm going to add 1 here. I'm going to have 5 over 5x to the 4th over 4. I'm going to add 1 here, so that's going to be 2x to the 3rd over 3. And then this is just a -1. It's not a big deal. And I'm going to add 1 to here. This is already x to the 1st, so it's going to be x squared. So I'm going to have x squared. I'm going to divide by 2. And this is a constant. So the constant of variation, remember, this is just x is a 0, so I'm going to have 7. I'm going to add 1 to it. So I'm going to have 7x to the 1 divided by 1. Well, I don't need to write the divided by 1 part. So this is my answer to this antiderivative of this function. Alrighty, I'm going to go ahead and save this and work on the next video where I'm going to do maybe undoing the chain rule and the quotient rule and things like that. Okay, here we go.